Hey, science fans! Welcome to another exciting journey into the fascinating world of science. Whether you're a curious student, a lifelong learner, or just someone who loves to discover how things work, you're in the right place. Today, we're about to embark on an adventure that will change the way you think about something you experience every single day: heat. Our topic is calorimetry, the science of measuring heat. But what does that really mean? Calorimetry is all about understanding how energy moves from one object to another, especially in the form of heat. Scientists use special tools called calorimeters to measure the amount of heat transferred during chemical reactions, physical changes, or even just when you mix a hot and a cold drink together. It's a field that helps us answer questions about everything from cooking to climate change. Have you ever wondered why your hot cocoa cools down if you leave it on the table? Or why an ice cube feels so cold when you hold it in your hand? These everyday mysteries are all about heat transfer. Heat is always on the move, flowing from warmer objects to cooler ones until everything reaches the same temperature. That's why your cocoa loses its warmth to the air, and why the ice cube steals heat from your hand, making it feel chilly. In this chapter, we'll explore how different things cool down or heat up, and why some materials seem to change temperature faster than others. We'll look at the energy needed to melt ice, boil water, or even just warm up your lunch. You'll see that not all substances behave the same way when it comes to heat. Some soak it up quickly, while others take their time. We'll also discover how scientists use these ideas to design better materials and solve real-world problems. To kick things off, we'll travel back in time to meet one of the greatest minds in science, Sir Isaac Newton. You might know him for his work on gravity, but did you know he also studied how things cool down? Newton's law of cooling helps us predict how quickly an object will lose its heat to the environment. His discoveries laid the groundwork for much of what we know about heat transfer today, and his curiosity continues to inspire scientists around the world. Next, we'll dive into the difference between heat capacity and specific heat capacity. These might sound like complicated terms, but they're actually pretty simple and super important. Heat capacity tells us how much energy it takes to change the temperature of an object, while specific heat capacity is all about how much energy is needed to heat up 1 gram of a substance by 1 degree. We'll use everyday examples like heating up metal objects or cooking food to make these ideas crystal clear. Finally, we'll uncover the secret world of latent heat, the hidden energy involved in phase changes. When ice melts into water or water boils into steam, energy is being used, but the temperature doesn't change until the phase change is complete. This hidden energy is called latent heat, and it's the reason why melting ice or boiling water takes longer than you might expect. Understanding latent heat helps us explain everything from weather patterns to how refrigerators work. So, are you ready to turn up the heat on your knowledge and become a master of calorimetry? Grab your curiosity, put on your thinking cap, and let's dive into the amazing science of heat together. Let's go! Let's start with Sir Isaac Newton's insight on cooling. Newton, one of the greatest minds in science, wasn't just interested in gravity and motion, he was also fascinated by how things lose heat. In the late 1600s, he observed something simple yet profound. When you take a hot object and place it in a cooler environment, it doesn't just cool at a steady rate. Instead, the rate at which it cools depends on how much hotter it is than its surroundings. The bigger the temperature difference, the faster the heat escapes. This became known as Newton's law of cooling, and it's a principle that quietly shapes our everyday lives, even if we don't notice it. Think about it. When you pull a steaming bowl of soup out of the microwave and set it on the kitchen table, it seems to cool down rapidly at first. That's because the soup is much hotter than the air around it, so heat rushes out quickly. But as the soup gets closer to room temperature, the cooling slows down. The temperature difference shrinks, and so does the rate of heat loss. This is why your soup might go from scalding to warm in just a few minutes, but then takes much longer to reach that perfect, just right temperature for sipping. Imagine 2 cups of hot chocolate, one boiling hot, sending up thick clouds of steam, and the other just pleasantly warm, with only a gentle wisp rising. If you set them side by side in a chilly room, the boiling cup will lose its heat much faster at first. The difference in temperature between the boiling chocolate and the room is huge, so the energy transfer is rapid. The warm cup, on the other hand, cools more slowly because it's already closer to the room's temperature. This simple observation is at the heart of Newton's law of cooling. If you could watch a time-lapse of that boiling cup, you'd see the steam fade quickly at first, then more slowly as the drink cools. The process isn't linear, it's exponential. That means the rate of cooling drops off as the temperature difference gets smaller. This is why, if you're in a hurry to drink your hot chocolate, you might blow on it or stir it to help it cool faster. Both actions increase the rate of heat loss by moving cooler air over the surface, temporarily boosting the temperature difference. This principle is everywhere, like when cookies cool after baking. Pull a tray of cookies from the oven, and you'll see steam billowing off them. The kitchen fills with that delicious aroma as the cookies rapidly shed their heat. The hotter the cookies are compared to the air, the faster they cool. Bakers know this instinctively. If you want cookies to cool quickly, spread them out on a wire rack so air can circulate all around, maximizing the temperature difference and speeding up the process. As the cookies approach room temperature, the steam fades and the cooling slows down. The process becomes more gradual, and the cookies settle into their final texture. This slowing of the cooling rate is a direct result of Newton's law. It's why after a few minutes the cookies are safe to touch, but they might still be a little warm inside. The last bit of heat takes the longest to leave. In scientific experiments, especially in chemistry and physics labs, this principle is crucial. When scientists measure how much heat is produced or absorbed in a reaction, they have to account for heat lost to the surroundings. This is called a cooling correction. By understanding how quickly an object cools, researchers can adjust their calculations to get accurate results. Without this correction, measurements would be off, and experiments could give misleading answers. Forensics uses this to estimate time of death by measuring body temperature. When investigators arrive at a crime scene, one of the first things they do is check the temperature of the body. Since a body cools after death, following Newton's law, scientists can estimate how long it's been since the person passed away. They compare the body's temperature to the surrounding environment and use mathematical models to work backward in time. Of course, real life is messy. A body cools following Newton's law, but investigators must adjust for factors like clothing, body size, air movement, or if the body was in water, which speeds up cooling dramatically. Even the weather and humidity can play a role. By carefully considering all these variables, forensic scientists can provide a more accurate estimate of the time of death. So, from your kitchen to the crime lab, Newton's law of cooling is quietly at work, reminding us that science is everywhere, shaping the world in ways we often take for granted. Have you ever wondered why your pizza slice seems to cool off so much faster than the rest of the pie? It's not just about the temperature of the room or how long it's been sitting out. There are several fascinating factors at play that determine how quickly your food loses its heat. And understanding them can actually change the way you think about everything from leftovers to your morning coffee. One important factor is the nature of the surface. For example, a black rough object radiates heat much faster than a shiny smooth one. This is because dark, matte surfaces are better at emitting infrared radiation, which is a key way heat escapes. That's why a blackened baking tray cools off more quickly than a shiny metal one, even if they started at the same temperature. But surface isn't the only thing that matters. The difference in temperature between your food and its surroundings is also crucial. The bigger the gap, the faster the heat will flow from the hot object to the cooler environment. That's why a steaming pizza slice cools rapidly when you set it in a chilly kitchen, but much more slowly if the room is already warm. The material your food or its container is made from also plays a big role. Metals, for instance, are excellent conductors of heat, which means they transfer warmth away from your food quickly. Wood, on the other hand, is a poor conductor, so it keeps heat in for longer. That's why soup in a metal bowl cools faster than in a wooden one. But perhaps the most important factor is the surface area to volume ratio. When you cut a pizza into slices, each slice has more surface area exposed to the air compared to its volume. This means there's more space for heat to escape, so the slice cools down much faster than the whole pie, which has less surface area relative to its mass. So next time you grab a hot slice, remember, it's not just the temperature, but the surface, the material, and especially the shape that decide how quickly your food cools. That's the science behind why your pizza slice loses its heat so much faster than the whole pie. Surface area to volume ratio explains much. A big ice cube has less surface area than crushed ice, which melts faster. Cooling fins on engines increase surface area for efficient heat transfer. In nature, desert foxes have large ears to dissipate heat, while Arctic foxes have small ears to conserve it. Spreading mashed potatoes increases surface area, cooling them faster. It's physics at the dinner table. Heat capacity is the energy needed to raise an object's temperature by 1 degree. A big object like an ocean has a high heat capacity, moderating coastal climates. A small puddle heats quickly, while a large pool absorbs more heat with little temperature change. A cast iron skillet has high heat capacity, staying hot longer, while an aluminum pan heats and cools quickly. Specific heat capacity compares materials. It's the energy needed to raise 1 kilogram of a substance by 1 degree. Water has high specific heat capacity, absorbing lots of energy with little temperature change. Metals heat quickly due to low specific heat capacity. At the beach, sand heats fast, but water stays cool. Water's high specific heat capacity makes it an effective engine coolant. Latent heat is hidden energy used in phase changes like melting ice or boiling water. Adding heat to ice at 0 degrees doesn't raise temperature, it melts the ice. At boiling point, added heat turns water to steam without temperature change. Steam burns are dangerous due to latent heat release. Sweating cools you as evaporation absorbs latent heat from your skin. Zoom in to see latent heat at work. In ice, molecules vibrate until bonds break, turning solid to liquid. In water, molecules move faster until they escape as gas. Latent heat of vaporization is greater than fusion, requiring more energy to turn liquid to gas. Refrigerators use this principle, with refrigerant absorbing and releasing latent heat to cool interiors. It's a cycle of energy transfer, not magic. It's physics. We've journeyed from Newton's cooling law to latent heat's molecular dance. Calorimetry is everywhere, from cooking to weather prediction. Science reveals the universe's hidden rules. Keep asking questions and exploring. Visit WANA Educational Services for more fun lessons and resources. Join our community of learners and follow us for daily tips and updates. Thank you for joining me today, science fans. Keep exploring, keep questioning, and remember, science rules.